here's the idea. Here's my space W, two-dimensional plane through the origin. I've got a vector 1, 2, 3 out like this. And what I want to do is find the projection of that vector onto W. Another way to say it is I want to find the point in W that's closest to 1, 2, 3. Or another way to say it, if this is my vector B, I want to find the parallel component. One thing I know is that anything in W can be written as a linear combination of these two vectors. 3 over 2, 0. The second one. Is that something positive? So if I could just figure out the scalars to use for each of these vectors, I could build the point in W that's closest to 1, 2, 3. Do you know how to find a scalar? Yeah, this is really what the dot product was invented for. All those other things just fall out. This is why we like the dot product. So I'm going to go 5 over root 10.
Yes.
And the number that goes here is my 1, 2, 3. So let's see, that is 15 and 6 is 21.
B dotted with U1 and B dotted with U2.
You got it. You want me to do the arithmetic? So I could multiply and add a bunch of things together, make it look nicer. Trust your abilities on that. Find a matrix C such that V is the column space of C. That's pretty straightforward. And what do you think a better basis to use? Was that original one or the new one? Yeah, I like the new one. Oh, yeah, I'm going to go with the new one. And that's going to help me out for the next problem. Oh, my bad. No, V's the plane. Oh, so I call it W. This was
We're doing part.
V. You're doing part. Okay, so V is this two-dimensional plane. The basis for this two-dimensional plane is given right here. That's what we did in the first couple parts. And so to say this is a basis.
Yeah.
And so this matrix, the column space of this matrix, is all the linear combinations of the columns, which is equal to all the linear combinations of the vectors.
Yeah. I was just getting confused because I was thinking of V as the vector 1, 2, 3,
Got it.
not as the.
So what we thought was here was V parallel,
V parallel.
and V parallel was the projection of 1, 2, 3 onto the plane.
Yes. What was the last thing you want us to do?
Find QR factorizations.
Yeah, let's see. Oh, yeah, I should have started with it. Oh. I agree with you. So, let's make C equal to, yeah, lost probably. What were the two vectors originally? What was the first column?
3, 1, 0.
And,
Negative 2, 0, 1.
and then, we want to write this as a QR. What are the columns of Q? That's exactly what we had there. So if I do-
C, such as V, the column space of C, that was.
Yeah, I decided to go with this instead. So both of these are acceptable answers to that question.
Okay.
And what I was really trying to get you to do with this question is give you a QR factorization. So I want you to see that those two matrices both have the same column space. And then R is essentially the matrix that fixes, that turns this matrix into that one. Okay, one way to find the R matrix, oh, actually, first of all, what do we know about R? What shape does it have? It's upper triangular. So that means I know that this is going to be a 0. And there's going to be 3 numbers there. So one way to do this is to just go through and there's places in, oh, actually, you can kind of see this actually. So there's places in the calculation for the Gram-Schmidt process that gives us the numbers. I'll just talk about where this number comes from, and then I'll do the rest by the shortcut. So remember, the correct way to think about matrix times column is these guys are going to be the vectors we think about, and the scalars are going to come from here. So this number is going to hit that, and this number hits that one. And what I'm trying to do is turn some combination of those two vectors into this. So how many of the first column do I need? You see the square root of 10 plus 0 of these gives me the 3, 1, 0. And so is this number comes up as the magnitude of the original column. And then it's going to turn out this number comes up as the magnitude of the W perp. And this number is going to be how much we scale this one by to build that. Let me show you the shorter way to do this. It's, if I do, let's talk about it this way. Q transpose times Q. So remember, Q transpose is write the matrix sideways. Yeah, the bottom right is magnitude W perp. And the top right is the scalar to turn U1 into W2 parallel. But watch what happens when I do Q transpose times Q. Is you see that as I'm doing the finger shortcut for this, I'm just doing the dot product of these two vectors, or that vector with itself. Given this unit vector, what's the dot product of that vector with itself?
1.
When I do the finger shortcut for the top right, I'm really just doing the dot product of these two, and that's going to be 0. The dot product of these two again is going to be 0, and that's going to be 1. So if I multiply both sides here by Q transpose, is these cancel out, because it's just that matrix times the 1, 0. So the way to calculate R is to just do Q transpose times C. And if you work that out, you you'll end up with, this is square root of 35. And you remember the scalar we used, was it negative 6 over square root of 10? I think this is what it'll end up. If you multiply this out, that's what you should get.
So R before Q
So
to say R.
R is Q transpose C. Yeah, so the real relation is C is Q times R. And then we move this Q to the other side, Q transpose C is R.
And when you move it to the other side, you're taking its inverse. It's zero.
Oh, yeah, the nice thing is Q transpose is Q inverse.
Okay.
Oh, actually, it's a little bit careful. We only have inverse, so a little bit more of that. We only have the inverses for square matrices. So we actually call that a left inverse. And I was avoiding that word because I guess I don't want to use the word inverse here because it's not square. So if I multiply the left side of Q by Q transpose, I get the 2 by 2.
So define Q transpose by the
No, by Q, so Q transpose is just this matrix where I read out the column.